Welcome to Maths with Bob. Today we're looking at the hyperbola, part of the Conics video series, and I just thought I'd show you, we'll rotate this plane and you can actually just have a quick look. This is the hyperbola, okay, with eccentricity 1.304, a bit nearly like one of the examples we're going to be looking at. And you can see here that we can, in GeoGebra, we can just rotate this plane and just have a look how it's cutting the conic sections. And just while we're on this, obviously the angle, the slant edge, if the slant edge was at the same angle as the plane, we would create what's called parabolas. But as you know, eccentricity for hyperbolas is in fact greater than 1. Okay, and root 2 for the rectangular hyperbola. Okay, well, we hopefully can see that the hyperbola is just a conic section, and it has an eccentricity which is larger than 1. If the eccentricity is 1, it's a parabola. Obviously 0, it's a circle. And root 2, it's actually what's called a rectangular hyperbola, where the asymptotes are actually at right angles. And we're going to be looking at that later on, a special case of that one, xy equals c squared. But at the moment we're looking at just the ordinary rectangular hyperbola. X squared on a squared minus y squared on b squared equals 1. And you can see there's a different orientation. Y squared on b squared minus x squared on a squared equals 1. And the asymptotes y equals plus or minus b on a x. Okay, and we can see the foci will change plus or minus a e 0 or 0 plus or minus b e. And anyway, we'll have a look at those. But we also can represent a hyperbola by its parametric form. X is equal to a sec theta and y is equal to b tan theta. That's the parametric representation for the hyperbola. Okay, now, as we know, the eccentricity is larger than 1. How do we find the foci and directrices? Well, we have to do the internal and external ratio as we did for the ellipse, and basically solve some of these equations simultaneously, and you'll find that the foci are where they should be, as they are for the ellipse, plus or minus a 0, and x is equal to plus or minus a on e for the directrices. Okay, now to find e, you do the same sort of thing as you do for the ellipse. But now, instead of b squared being equal to a squared 1 minus e squared, it's actually b squared equals a squared e squared minus 1. You can just notice that the e squared and the 1 have changed places, okay, for the hyperbola. Okay, and if you want to, here's some quick examples on finding the eccentricity. Okay, you can see here x squared on 9 squared minus y squared on 8 squared. Okay, we use the eccentricity formula. Okay, e is equal to the square root of 1 plus b squared on a squared. And we can get the foci and directrices fairly easily. And these two are not symmetrical. You'll notice I put a special note there that the second example is actually not y squared on 8 squared. It's actually y squared on 9 squared minus x squared on 8 squared. That gives it a different eccentricity, and actually makes the asymptotes y equals plus or minus 9x on 8, as opposed to y equals plus or minus 8x on 9. Okay, and you'll notice I've put in a little quick note there about finding the foci quickly with using a squared equals, a squared plus b squared equals c squared, or if you like, c squared equals a squared plus b squared, where the foci are at plus or minus c0. Okay, so let's move along. Okay, so we now obviously have to go into a lot of the theory about the tangents and normals, and I don't go too much about normals, but we look at the equations. We have to differentiate the hyperbola implicitly, and you can see here we get dy dx is equal to xb squared on ya squared. And then we have to get what's called the Cartesian gradient by putting x1, y1 in, and the parametric tangents gradient by putting the a sec theta and b tan theta. And you can see here I've actually found the negative reciprocals to find the normals, the Cartesian normal and the parametric normals gradients. Now, what we do with these obviously is we to find, you can see here, Cartesian tangents. Well, we obviously just have to put the Cartesian gradient in and then try and simplify it. And you'll notice we have to divide by a squared b squared, and use the fact that x1 squared on a squared minus y1 squared on b squared is equal to 1, which is actually on the hyperbola. And you can see here the tangents equation is very similar to the one for the ellipse. It's x1 on a squared minus y1 on b squared equals 1, and as you know, you might remember the ellipse had a plus there. Okay, then we go into the normals, and again you have to multiply this out and divide by x1 y1, and you'll get a bit of a different normal equation. A squared x on x1 plus b squared y on y1 equals a squared plus b squared. You might remember there was a minus there for the ellipse and a few different things. Okay, here we go. Now the parametric, the tangent, obviously you can see here is a sec theta on, x sec theta on A plus y tan theta on B. A sec theta and B tan theta are the parametric points. As you know, you just substitute them into the y minus y1 equals mx minus x1. And you do the same sort of thing. You use the negative reciprocal. And okay, you've got to now divide by sec theta tan theta for the normal. And eventually you'll get ax on sec theta plus by on tan theta equals a squared plus b squared. Okay. So the next is the chord of contact, and we do a similar sort of thing for the chord of contact. We just put the x1 and y1 and x2 and y2 on the tangent, and since they both lie on an equation which looks like x0x on a squared minus y0y on b squared equals 1, we know this is the equation of the chord of contact. It is quite messy to do this algebraically, and that's why most textbooks just do it this way. Now while we're here, I'll just show you. This is actually the chord of contact. This is again in GeoGebra. If you come and you can see here, if I push up here, we have the equation of the chord of contact. I'll just pull it across a bit so that it's on both branches. We can actually push the point P, just pushing the point P up close to the particular branch, and you can see the chord of contact is actually inside that branch. Okay, so it depends on how far away we are, I guess, if you like. Okay. Alright, so let's, now the final little part is a little bit about the chord and some of the properties. And now you can see here, this is a chord, the parametric chord. These are always messy to derive. You'll see here, I've actually, if I can just have a quick look, if I can find a pen. Okay, here we are. So you just have a look here. Okay, I've got to actually expand that cos part out as cos A minus B, and I'll get a sine part which will drop out. This part here will just drop out, on the expansion of this part here, and it basically gives us this expression here, which is basically this expression here. But and you can see here it does get a little bit messy, but the chord, the parametric chord, if you like, basically is now x on A cos theta minus phi on 2 minus y on B sine theta plus phi on 2 equals cos theta plus phi on 2. Okay, alright. Now, finally, I'm just trying to go on to the next page. Here we are. There are some of the geometric properties. Now, the geometric properties are a bit similar to the ellipses, and you can see here we have now, instead of the sum, the difference of focal lengths is constant. We have the tangents bisecting some angles internally, and the normal bisecting an angle SPS dash, which is the other focus, externally. Okay, and again we have a similar sort of idea as the chord of contact from a focal a point on the directrix is a focal chord. So okay, so let's actually now I didn't actually set up an example here, but you can actually show this sort of thing as well for the hyperbola. And then we have another sort of similar sort of property. The part of the tangent between the point of contact and the directrix subtends a right angle at the corresponding focus. So you have these sections subtending right angles, as you did for the ellipse. Okay, well, thank you for watching, and bye for now.